My name is Tim Davis, and I'd like to share with you the beauty of mathematics. This work was presented at the Art and Engineering exhibit at the Harn Museum in October 2011, and it's in collaboration with Dr. Hu at AT&T Research.
Why is Beethoven's Ninth Symphony beautiful? If you don't see why, someone can't tell you. I know numbers are beautiful. If they aren't beautiful, nothing is. Erdős was a brilliant mathematician of legendary eccentricity who had many collaborators here at the University of Florida. I love this one. Where there is number, there is beauty. Proclus was a 5th century AD Greek mathematician and philosopher. So math is true, but do you know it? Math is beautiful, but can you see it? Let me illustrate it for you. Say we have 4 equations and 4 unknowns. Not every equation involves every unknown. So this gives the set of equations an interesting structure. A mathematician would see it and say, ooh, that's beautiful, but do you see it? Well, we can show it this way as a matrix equation, ax equals b. Now the coefficients of each equation can be placed in this 4x4 matrix, and the 4 equations can be written as this ax equals b equation. Now, consider the matrix structure. Where are the non-zero values? What equation involves which unknowns? And it looks like this. So put a dot here where the non-zero values are, and put numbers 1 through 4 down the diagonal, just for reference. Now you see there's a dot here between 1 and 2, or sorry, 1 and 3. So they're related to each other. So draw a circle for each equation, and draw a line from equation 3 to equation 1 because they like each other. But 1 and 2 do not. So there is no line from 1 to 2. So this draws a picture of how, called a graph, of how these equations are related to each other. But is it beautiful? Is this the right picture for these equations? Where does the number 1 live? Where is the home for 3? Put it on a piece of paper. Where? Let's find out. Here's 3 different ways of drawing the same relationships. They're all equivalent, but they're drawn differently. Now I would argue that the one here on the bottom left is the most beautiful, or at least the most scientifically interesting, because it tells you that nodes 2 and 4 are in a way equivalent. They're both talk to 3 and they're both equidistant from node 1. Whereas this one sort of gives preference to node 2. It's close to 1, but 4 isn't, but they're the same. Okay. So, well, that's fine for 4 equations and 4 unknowns. But if you had 100 people and had to draw them on a page and draw lines between them if they liked each other, where would you put the people? You might get this rat's nest. Is it beautiful? Well, maybe in an abstract sense, but what it certainly does not depict is that there is structure in these equations. There's a structure in these relationships. You can't see it. It's not beautiful. It's hidden. There's structure, but it's hidden in a random jumbling of the node positions. So, to compute aesthetically pleasing positions for the nodes, we make a pretend game on the computer. It's simulated. So let each node have a electrical charge. So nodes like to push each other away. They both have positive electrical charge. And now for every line, make a line a spring. So the springs like to bring them together. So if you had just 2 of these, the charges push each other away, but the spring brings them together, and they then go into an equilibrium of a minimum energy state. Okay, now add a 3rd, or a 4th, or 557,000 of them. And this is what you get. And now, is it beautiful? The physics is telling you how these relationships should appear. So we can do this on bigger equations. Now, some equations model, so there's the final result, that was previously hidden with the random jumbling. Now, some equations model a real physical object. And if you were to draw them, you know where they go. because it represents the real object. So this is several thousand equations, but every node has a place in space. It has a home because, oh, I wrote that equation down to model that part of that helicopter right there, so I know where to draw it. So, well, what if you didn't know where to draw it, and you let that sprawling and wobble effect find where to draw it? This is what it might look like. So here, now next, to show more relationships in the structure of the graph, we can color the edges. So let me take a close-in view. And here, the shorter edges are colored orange or yellow, and some of the longer edges in shades of blue. And then the typical edges are green. You can see here some orange edges, and here blue, and here green. So this is the helicopter. You see up here the rotors of the helicopter. You see the nose cone, the landing gear, and the tail. Well, you can do this with the systems of equations that don't have a place. All these problems come from sparse matrix computations, a matrix that has holes in it, basically. These equations arise in many applications, and the whole point of the slide is that you cannot read it, it's too busy. There's far too many to list here. Some have natural two-dimensional and three-dimensional structure of where the nodes should be, like the helicopter. Or problems in computational fluid dynamics. Where will the air flow? Where was fluid flow? Structural mechanics, heat transfer, semiconductor simulation. All these equations have a place in space. Others don't. Like, for example, compute the Google PageRank. Well, you have a web page, and a web page, and a web page. What's important is not where. Is a web page live here? Or does it live over here? Or maybe over here? Where do you draw a web page on a piece of paper? What a silly question. What's important is how the web pages are related to each other by the web links, by the links between them. So, likewise, in the next example, a system of equations can be written to, say, optimize your financial portfolio. This is one. So the equations are based on probabilities of different outcomes of different future events. Well, what happens if stocks go up, or interest rates go down, or this, or that? And in all these different scenarios, you want your portfolio to be somehow stable, and over all possible outcomes, give you a good return. Well, so where is a stock? Where is a bond? Where's your CD? Oh, it's in the bank. Where's your bank? It doesn't matter where the bank is physically, but how are these economic decisions related to each other? They have no natural position on a 2D piece of paper. Now this matrix has not just 4 equations and 4 unknowns, it's a little bigger. It's 37,000 equations and 37,000 unknowns. That's actually fairly small for matrices as they go. So a physics-based rule is essential if you have a graph this big and we want to visualize it, but it's also beautiful. This image here appeared in the most recent issue of the Harvard Advocate. And here's a close-up view of 2 of the different financial scenarios. So what I'd like to do next is to give you a tour of a few of the most beautiful images in the 2,547 matrices comprised of the University of Florida Sparse Matrix Collection. So here is Schwung-Wabel, I call it. It's a Hessian matrix, fittingly, from a quadratic programming problem, which is to find the best solution to a system of equations. And there's a close-up of the relationships between the equations inside a matrix. And who knew that math is beautiful? This red fish, no, it's not a red fish. I didn't put this up I didn't get this matrix as, oh, here's a red fish. No, this is a semiconductor circuit simulation. And the green underneath is the circuit. And the lines that come out of it are what happens at that circuit position in different frequencies. And it just happens to look like a cool red fish. This graph is larger. This one has 660,000 nodes. Here's a bluefish. Well, it's a linear perking optimization problem. And a close-up. And stay around for poetry. This elegant mesh represents the fluid flow in a shallow bay of water. It could be used to simulate, for example, where the pollutants would flow. But it also looks like it looks like a shimmering fishnet, simulating a bay of water. The reason you see little hexagons there is because the shallow bay is divided up in little triangular cells of water, and the cells connect to each other in a hexagonal structure. This mesh is regular, unlike some of the others, because the problem being modeled has a natural underlying 2D or 3D structure. Here, the lines are so close together, they seem to form a solid surface, but it's not. It's just a set of lines that connect the many equations. It's not a surface. And here you see a valley in between. This is a structural problem. Here the graph reveals that the matrix comes from the discretization of a 2D or a 3D object, just like the Comanche helicopter. And here in this close-up, you can see the regular 3D mesh. This is a fireworks display. Oh no, it's a linear programming optimization problem. And there's a close-up. And math is beautiful, isn't it? This one I call web poppies. So we have 512 people and 394,792 web pages. Draw a line between a person and a web page if that person likes that web page. Okay, so where do you draw the people and the web pages? The Sheboygan and Wobble simulation tells you. And what you see here in the close-up, here's, say, a person. And here's a bunch of web pages that that person likes that nobody else likes. That's the poppy. But they also like a lot of web pages that lots of people like, and that's the massive red in the middle. This one is the United Kingdom, well, minus Ireland. See Wales at the top. The Sheboygan and Wobble physics doesn't know anything about north or south, east or west, so it's got the island flipped. This is Scotland to the left, and Wales to the top, where my ancestors come from. And here's Scotland, where my postdoc advisor comes from, who also does matrix computations. This graph is fun. It looks like something out of Dr. Seuss, doesn't it? But it's not. It's an airline crew scheduling problem, mapping hundreds of crew to thousands of commercial airline flights. So you're an airline company, and you have to come up with a schedule, the crew schedule, that maximizes profits while satisfying certain constraints. For example, a pilot has a limit on the number of hours that can be flown and spent in a cockpit in a given week. Also, it's typically not permitted for a pilot to fly two planes at the same time. Okay, so you have this system of constraints that gives you a system of equations. You want to find the best schedule when you get an equation, a beautiful equation that looks like this. This sphere is a simulation from quantum theory. It's quantum chromodynamics, and it's a high-dimensional cube or sphere inside here that's all nested, layered on top of itself, that turns into this sphere with this Sheboygan and Wobble physics simulation. And here's a close-up. This one, if I hit the caption, inside the human bone, you might guess it. It comes from a matrix that simulates the forces and stresses on the human bone. And not surprisingly, the graph looks like a bone. So this graph is a bit larger. It has about 1 million nodes and 200 million lines in this picture. 200 million edges between nodes in these equations. And there's a close-up. And it looks like there's little cells there, but it's not. It's just equations and their relationships. This is a helicopter rotor with 4 blades connected by some kind of complex control structure in the center. It looks like a spider with fuzzy legs, doesn't it? And there's a close-up. So this one, take a slice of an airplane wing and put a mesh where the air is, and the hole in the middle is the wing itself, because you don't care about the wing. What you care about is how does the wind flow around the wing. You want to know how much lift you get for your airplane. And you get this beautiful picture, and there's a close-up of it. You can see underneath it's a regular mesh because you want to put equations regularly through space. This one's called a tokamak. It's a device that creates an intensely strong magnetic field that contains high-temperature plasma in a torus or a donut to harness fusion power. So that's where the fusion would occur. This problem represents fluid flow around a fixed object placed inside a cylinder. The object is in the middle, and then the boundary conditions, the cylinder wall, are little hair-like follicles around the edge of the graph. This picture appears in the October 2010 issue of IEEE Spectrum, a scientific trade journal. And here you can see the mesh underneath. So math is both true and it's beautiful. Can you see it? Well, so you've seen now math translated into art, but where does the math come from? Well, Erdős was very fond of quoting his mathematician friend and colleague as saying, a mathematician is a device for turning coffee into theorems. And there's a wordplay in the German, Kaffee turned to Satz, which is German for theorems, and the word for coffee grounds in German is Kaffeesatz. So, to explain to you where the math comes from, I'm going to talk about coffee. So, an eau de caf, I think I'll cue. Espresso caf, I think I'll brew. Oh no, decaf! The task is in blue. Alas, the gaff, you see I'm blue, my output math is cut in two. No calf, I have. Math. Brew. Ah. If you're not in the wrath, the one I'll stew. With half and half, try two I'll do. A cup of calf I shall imbue. To turn the calf, equations glue. To the maths, and Erdős too. From calf to math, the theorem's true. Now I'd like to share a second of two poems, a translation of a deep and passionate, yet inaccessible poem. Robert Burns' poem is the origin of the phrase, the best laid schemes of mice and men go oft astray. So just like pure mathematics, the Scots dialect of Burns can be hard to understand. As I read the original poem, you can listen to the Scots dialect and follow along with English subtitles. So the original will be on the top left of each slide, and you can read along the English paraphrase on the bottom right. So I'll first read To a Mouse and then the Gator translation. So To a Mouse by Robert Burns. Wee slicket, clorin, timorous beastie. Oh, what a panic's in that breastie. The need to start away, say, hasty with bicker and battle. I would be loath to rim and chesty with murder and paddle. I'm truly sorry, man's dominion has broken nature's social union and justifies that ill opinion that makes thee startle at me, thy poor earth-born companion and fellow mortal. I doubt no else, but thou may thieve. What then? Poor beastie, thou may live. And I may live in the thraves, a small request. I'll be the blesser with the lave, and no the mist. That wee bit pussy, too in ruins. At city wilds the wind just blew. And nothing now the big and new in a foliage green. Bleak December's winds and soon, and snell keen. I saw the fields laid bare and vast, and weary winter coming fast, and cozy here, beneath the blast I fought to dwell. Till the crash the cruel culture passed out through thy cell. Ah, wee bit heap by leaves and stibble has cost thee money a weary nibble. Now thou'st turned out for all thy trouble, but house a hull to thaw the winter's sleety dribble and Clonach cull. But, mercy, thou art no thy lane in proving foresight may be vain. The best laid schemes, mice and men, gain yet to glide, and layest naught but grief and pain upon us judge. Still, thou blessed compared me, present coming to be. But I backward cast my eye on prospects drear, and forward, though I cannot see, I guess and fear. Hard to understand, wasn't it? You probably would not have followed what I said without the English subtitles. So to better understand the deep thoughts and passions of Robert Burns, follow along with me as I read a translation that describes the effect of budget cuts on the Gator Nation. Burns' poem will be on the top left as before, and I'll read the Gator translation on the bottom right. So, from a mouse on turning her up in a nest with a plow, to a gator on cutting him up in a swamp and how.
We speaking good, timorous gator. Oh, what a panic sooner or later when Tallahassee's common action tax thy budget. Oh, what departments, legislature, you'll tell, no budget. Oh, it's truly sad. The state's dominion has broken nature's social union and justifies the Pope's opinion that makes them throttle me or faculty, companion, and fellow mortal. I don't know else, but I may teach. What then? For a gator, I'll beseech a 50 million. This series, it's a small request from politicians' glorious speech that never missed. Now we live spoken to in the ruin. It's what storm majors winter strewn. And nothing now they take a freshman a cash once green. And Bernie Mansions has their forcing. Cut sharp and keen. Thou saw the academic fields and thought thy future's bright to yield and cozy here with cups that healed, thou hope to say, till crash your sutures bleak and heel cuts fell and fade. Ah, we the heap of profs and majors has cost them money. Legislatures have turned me out and skinned a gator with hearts turned cold. Perhaps they hope to hear thee later, if breath be hold. But, gator, thou hast known thy game, improving foresight may be vain. The best laid schemes of governed men gain laughter glide. Mayest know what grief and pain will promise pay. Still, thou art blessed compared with me. The President has cut me free, and with backward cuts his eye wells up in tears. Yet, forward, look, and clearly see election nears. Thank you very much for your kind attention. For your kind attention, can I entertain any questions about the poetry or the math or the mathematical poetry? Yes.
The math that you produce in the art has beauty in it. Does it have anything that goes beyond the beauty? Is there any practical applications that can come out of those?
Of the visualization. So the question is there any mathematical or academic scientific interest that comes out of the visualizations? Well, these visualizations were put together to help mathematicians and scientists and computer scientists like me understand the kinds of equations we're dealing with. So I write software and mathematical theory and methods for solving equations like this one. And when I write it, I have a picture in my mind as to what these equations look like. And the algorithms I write behave differently on different kinds of equations. And so I want to think about what they look like. That helps me write the software and develop the theory to solve these equations. So in an indirect sort of copy to math kind of way, they do. Only in a sort of inspirational sense, or only in a way that helps you get a sort of feeling for what the matrix equations look like. So in some sense, yes, not like a hard science, but sort of insight into what the problem structure is? It's a very good question. Thank you. Yes?
Is the way that you were lecturing today, is that something that you could expect in your classroom?
Oh, you can ask my students. Stand up, would you please? This is Carrie Holderman. She's in my class and she can vouch for the fact that there are times. It's very cool class. So I'm quite dangerous in the classroom. I tell R-rated jokes. I tell a joke and the class goes R. Yes.
I did have a question about the graphs. The one that shows the portfolio.
This one, yes.
So you want your portfolio to look pretty. Is there one that looks worse when things are going? I mean, you have projected as good.
Okay, what's happening in this picture, the equations are describing different, let me go to it, this one. The equations here are describing a sort of a path of possible outcomes. So in financial portfolio optimization, you want to ask the question, over all paths of future events, okay, I get maybe 1,000 different possible combinations of different outcomes. Over each of those outcomes, then, what will my portfolio do? And I want to optimize the sort of the best, the sort of average case scenario, and maybe mitigate against possible. So I can look at all these possible outcomes, and it's a balancing act of this, if I do this, if I do that. And so it's the beauty in the equation is not telling you, oh, it's beautiful, so now you have a good portfolio strategy. The beauty is simply in the decision structure as to making that decision. It's the structure of making the decision, not the decision itself. Does that make sense? Maybe?
Yeah, so you would have different scenarios of your portfolio.
Right, so if this one might depict, okay, if interest rates do something, or if rates go this way, or bonds go do something, okay, what will happen in each, like a decision tree, what happens in each outcome? And so this just is drawing a picture of the decision tree, the possible future events that could occur. And then you want to, now what's not being shown here is what happens at the leaves of this tree, if you will. What happens at the end of, it's not showing you the solution to your equations. It's just showing that how are these decisions related to each other. But very good question. If you're interested, by the way, in more, these are just a few pictures of 2,547 matrices in my collection. That you can find if you just Google Tim Davis at UF, you'll find these, and you'll find more poetry as well. Some of it's mathematical, some of it you have to have at least a bachelor's degree in math or computer science to understand. Some of it's very accessible. And it's got audio on it as well. So you can hear me do the Scots, and you can hear my postdoc advisor Ian Duff also do read the poem in true Scots. This is for, he doesn't like them. He doesn't like my accent. He thinks it's pretty lame. He tolerates me. Well, thank you. Oh, another question, yes.
So, it's kind of technical, but in drawing those graphs, from what I understand, those are basically graphs.
These are graphs, and they are drawn, yes, with this Sprung and Wobble physics model here. Yes. Let me put this over. Yes.
Is it only the connection that,
Yes.
the topology that matters, or do you take the numbers? And
The question,
inside the
yeah, it's a very good question. Is it only the topology or the connection between the equations that matter, or is it the numbers that matter? In this drawing, these drawings here, it's just the connections, the topology, how things are structured, who talks to who, that matters. When I went from this picture here, I threw away the numbers. I just want to know where the numbers are, which equations are connected to which equations, and that's what gives you the picture. I didn't use the values in the matrix to do anything. So I've thrown away information, actually. And then the color is just simply how tight the springs are. So this one, these you might draw red, but the longer ones might be green. Was there another question? Yes.
So the arcs are modeled with like spring
Yeah.
physics.
Right.
Do you ever run into situations where different like sets of characteristics for the string physics give you completely different kind of, optimal pictures?
Yeah, you can change parameters and get different pictures. Yes, we have some in paper we submitted, and it's accepted. Actually, it's going to appear in January or February of next year in the ACM Transactions on Mathematical Software, where we describe this process, and it's a paper describing UF Sparse Matrix Collection. It's a technical paper. It's not an art paper. It's got art in it. It's got stuff like this in it. But it's a technical journal article that describes, and it looks at what happens when these optimization of this sprung and wobble kind of simulation, what happens when it goes bad. And what happens when it goes bad is that pictures like this, you can take this and maybe twist it. Oops. Twist half of it, but not the other half. It doesn't look pretty. It's warped, it's mangled. So we have methods to get around that problem, which if I went into, I'd probably put to sleep everyone here but a few, even myself. Well, if there's any other questions, when it comes to me, talk to me individually, I'll be with my laptop at the table down. You can see some of these pictures. And if you want to see more pictures and more poetry, or even a video of this talk, okay, will be on my webpage, Google Tim Davis at UF, and you can find me and you can watch this talk all over again. Thank you very much.